And maybe we can get started.
Sounds great.
Yeah, I just pin like every individual of my student to join. Yeah, they might join later on. Yeah,
Yue is here. I saw him. Okay.
Sounds good.
Then let's start. Okay. So good morning, everyone. Thank you for joining this talk. Today, we will discuss the flow-based models and their structure-preserving variants. Right. So today's talk will be split into three parts. The first part is about conditional drift matching. In this part, we will discuss some general ideas behind conditional score matching, which makes the nowadays diffusion models to be trained efficiently. And then we will discuss how to use similar ideas to obtain other powerful flow-based models like bridge models or rectified flows. And then in part two, we'll discuss more about rectified flows. In particular, we will discuss how to use reflow to linearize the ODE drift for sampling. And in the third part, I will discuss some our recent researches on structure preserving flows. It's about how to make a flow-based model, like style transferring model, to be perfect equivariant, which will be super important in medical image analysis. All right, let's start from the part one, conditional drift matching. So before we discuss the general framework, let's quickly review nowadays diffusion models. So in every diffusion model, we will have a forward SDE that transform data distribution to a higher noise distribution, which is typically a sample distribution. And then we need to learn a reverse SDE to reverse this process to transform a noise distribution to a data distribution. And once we have this reverse process in hand, we can always sample Gaussian sample from the prior distribution and evaluate this reverse SDE to obtain some fake image fit in the data distribution. So in this reverse SDE, the only thing unknown is the score function, in particular the marginalized score function. And to learn this, we usually use a neural network to estimate it. So here in particular, we need to minimize some MSE loss, which we usually refer as the conditional score matching. And the expectation is taking over the first two sample X0 from data distribution, and then we sample XT from the transition kernel. And here T is sampled from some uniform distribution ranked from T0 to capital T. And why this conditional score matching is super easy to train? It is because we can always sample the couple X0, XT easily. And in particular, we can sample X0, like randomly draw a sample from data distribution. And since the transition kernel is known, which is basically a Gaussian distribution with mu t, the mean, and variance known in closed form, given the forward SDE, then we can basically sample this super easily. And we basically want to match some conditional score here, which is also in closed form and can be computed easily as well. Since everything is easily to be computed, we can train our score function super easily. Then a natural question we want to ask is that, can we extend the idea of conditional score matching to train other flow models efficiently? The answer is yes. Before we dive into the technical details, I want to start with the fact first. Let's consider a family of SDEs parameterized by some parameter theta, which follows some known distribution. And then we can consider a conditional SDE condition on this parameter theta with the drift, which is a function of that theta. And then our initial distribution is also depends on theta. And then we can define the PTXT condition on this theta to be the distribution induced by this conditional SDE. And we also define the marginalized distribution like this, which is just a natural definition. Then we can make a dual version of the SDE that have the conditional drift replaced by this marginalized version, which we can show that the XT induced by this SDE will simply follow the marginalized TTXT. Here I put the marginalized drift expression in closed form like this here, and which is basically the conditional expectation of the conditional drift. All right. One important fact I want to emphasize here is that this conditioned drift, this expected drift will no longer depend on the parameter theta. And we will use this fact afterwards to derive other diffusion models. All right. To better understand what does the expected drift means, here I give a very simple toy example. And for simplicity, I will set the diffusion coefficient to be 0 so that SD reduces to the ODE. Here we have two sets of parameters, which corresponds to the starting and end point of the drift. So first step, we have A1 and A2, and it corresponds to the red trajectory. And B1, B2 corresponds to the blue trajectory. And we have equal possibility to sample from, to get theta 1 and theta 2. And suppose we are at this point, all right? Then the only possible case to reach this point is to start from A1, and therefore the average drift will be the same as the conditional drift starting from A1. But if we are at this intersection point, then something will change because we have two possibilities now. We can either arrive this point by starting from A1 or start from B1 with the equal possibility. As a result, we need to average the drift at this point. As a result, we will get some average drift like this, which point to the left, point to the right horizontally. And this is the difference between the conditional drift and the marginalized drift. All right. So this is the part we have seen. So I have mentioned that one observation is that the marginalized drift will not depend on that parameter data. And the second observation would be that we can always find this marginalized drift by minimizing some MSE loss like this. And this is very similar to the conditional score matching. And to see why this is true, let's consider a simpler case. Basically, we see this in many undergraduate stats course. Basically, it says the mean of a distribution is always the minimizer of its second moment for arbitrary random variable x. And this is basically a similar case, just with some additional parameters. That's a quick note regarding the backward FDs. So in the previous two slides, we discussed everything in a forward process, but everything actually holds for the backward process as well. The only thing changed is that the forward Brownian motion will be replaced by a backward one. And we need to make some tiny change on the boundary conditions because we start from t equals capital T instead of t equals 0. And everything else will be exactly the same. All right, we are ready to view the diffusion model in another way based on that fact. So let's consider the process condition on a fixed starting point x0, which, well, we will sample from the data distribution. Then the forward process will be the same, but the backward process, since it's conditional on the starting point x0, the marginal score will replace by the conditional score. And the conditional score, as we have seen before, will take this form, but x0 is not known when sampling. Otherwise, we don't need to do sampling, we just report x0. So we need to deal with this x0 in some way so that we don't want the drift term no longer depends on it. So what we can do is like we want to replace this conditional score with some other term so that it does not depend on x0. And the good news is that we actually don't really care whether XT is sampled from this specific transition kernel. All we care about is that XT is sampled from the marginalized distribution. So what we can do, just apply the fact we just discussed by marginalize it over the starting point x0. And we will get this a little bit complicated expression. But we can simplify it a little bit and it will have this form. And the only thing we don't know is the orange term. And we will use a neural network to estimate it. As we mentioned before, we can always learn that marginalized drift using the so-called drift matching of loss objective. In particular, in our case, I will write it down in this way. And if we simplify it, we'll reduce it to the score matching, right? Okay, let's come back to the original question. That is, can we extend the idea of conditional score matching to train other flow models efficiently? The answer is yes, as I mentioned before. And from the lens of our more general framework, what we badly need is that we want to sample theta xt efficiently. And corresponding in the theta will be the starting point x0 in the score matching scenario. And then once we can sample this efficiently, we can basically sample the pairings in this MSE loss. And if we can calculate the conditional drift efficiently, and we can just train our neural network, Mutilda, to keep matching this conditional drift, and everything will be trained efficiently. All right, let's see some examples. So for simplicity, we always assume that the capital T equals 1. And in this example, we will assume that the theta will be a pair of samples from given data distribution. So for example, x0 can be a photo image, and x1 can be its blurry version. And we basically want to train a model to transform a blurry image into a clear one. And here's a simple example to show how it works. All right. If we follow the idea of score matching, we basically need a distribution path of xt that transform a blurry image x1 to a clear image x0. And in this case, we basically want PTXD given these two these two images to be sampled efficiently. And so and therefore we will have this coupling be sampled efficiently. So a natural choice to satisfy this requirement is the Brownian bridge. In this case, the forward process will have this expression, and this drift term will guarantee that 1t equals 1 will always end with b. And correspondingly, we will have a backward process conditional on starting point. And we will have the form like this, which is quite symmetric to the forward process, but we start from x1 equals b instead. And through some easy calculation, we can show that in this case, xt will follow a Gaussian distribution with the mean, which is a convex combination of the start and the end point, and have a very symmetric variant term as I shown here. Since we need to transform the samples in a blurry image dataset to the ones in a clear image dataset, we basically need to start from the conditional backward process. But in this formula, we have A unknown because it corresponds to a clear image, which we're trying to find. So we need to do some marginalization to remove the drift dependency on A. So in this case, we basically have two versions. The first version, we are only doing the marginalization over A, but we don't do the marginalization over the starting point x1 equals b. Then in this case, we will have the xt for some transition kernel starting conditional on that we start from some certain blurry image b. And in the second version, we basically do the marginalization over both A and B. And in this case, xt will be can be seen as a sample directly sampled from the completely marginalized distribution. And these two versions correspond to the DDBM structure and the image-to-image Schrodinger bridge structure, which are two famous papers about bridge model. Okay. So what's the major difference between these two architectures? So in version 1, we basically keep the coupling between x0 and xt, and in particular, when t equals 1, we will keep the coupling between x0 and x1. Well, in version 2, because we do the marginalization on both x0 and x1, this coupling will not be preserved anymore. So what will happen in practice? Let's consider the denoising process again, and we probably starting from the noisy image, say, of a bag or of a dog. And if we use version 1 implementation, it's guaranteed that we'll end with some clear image of dog. But if we use version 2 case, then there's no guarantee anymore. We probably start from a blurry dog image, and we will end with some clear cat image. So this is the major difference between these two versions. At the very end of this part, I want to discuss the limiting case of the version 2, when delta approach to 0. So when delta approach to 0, the transition kernel, which used to be a Gaussian distribution, will reduce to a simple linear combination of A and B. And if we're familiar with rectified flow, this is actually the rectified flow formulation. And visually, we will have the Brownian bridge, like for example, the red one, reduced to a dry, straightforward linear curve. And same thing for the blue one. And we will do the same trick as we did before by marginalization. I do the marginalization over the starting point A and B. Then we will have this expression. And if we plug this expression back to the backward version 2, then and do some simplification, then we will get the target flow in rectified flow, as shown here. So what does it mean? It basically means rectified flow is just a special case of the bridge model where we set delta to be 0. Okay. This is everything about part 1. Then in part 2, I will discuss more about rectified flows, especially reflows. A big fact here is that the marginalized drifts are usually curved. For example, in this toy example, when we marginalize the drift, we will have a high curvature at the intersection point. And this high curvature is harmful because it makes it super hard for the ODE solver to solve it. For example, let's consider Euler method, which assumes the local linearity of the drift. If the curvature is super high, then delta t must be super small to preserve the accuracy. And then the sampling process will become super intractable. So because of this observation, we want to find some way to lower the curvature. Before we try to lower it, we want to have a more formal definition of curvature first. So as we mentioned in our toy example, we noticed that whenever the conditional drift intersect, we need to do some drift average, then curvature happens, in particular at point C. And then the optimal drift matching loss I mentioned before will never reach 0 because we can never make our average drift to match all the conditional drift. In contrast, if there's no intersection, for example, at point D, then there's no drift average happened. Then we don't have curvature, and then we can show that the drift matching loss will reach 0 in optimal case. Therefore, to sum up, if we have a curvature, then the drift matching loss at this term will be greater than 0. And if we have no curvature at this point, then the drift matching term will be set to 0. So let's define the formulae. Let's use this fact to define the curvature of the entire trajectory formulae. So suppose we have a joint distribution of the couplings A and B, and then we can aggregate the curvatures or the optimal drift matching loss at all points to obtain a global measure of the curvature, as I shown here. And since in theory, the drift matching loss will be non-negative, we can show that if the global curvature measure reaches 0, then it will reach 0 at almost every point xtt. That basically means at almost every point we have 0 curvature, and we will always have the linear float. Okay. As a result, to obtain linear flows, we try to optimize the coupling Q to optimize this objective. But of course, at the same time, we need to satisfy some marginal constraint. In particular, we want the marginalization over B of Q to match the marginalization of the data distribution. And the same thing when we do the marginalization over A. This is because we want to always end with some sample of the data distribution when t equals 0 and when t equals 1. So the question now becomes how to update Q to lower the curvature. The answer is reflow. And here's a toy example. So originally, we have the coupling A1 matched to B1 and A2 matched to B2. And we can train a marginalized flow to estimate the trajectory. Then we can start from A1 and follow the trajectory, and we will end with B2 this time. And the same thing for the A2, we will start from it and we will end with B1. And then we can follow the flow to rematch the samples. And in the next iteration, the trajectory we induced will be linear. And we can keep redoing this for more complicated cases, and we can show that we will always end with some linear trajectories at the end. Note that the reflow method will naturally preserve the marginal constraints because we always start from a sample in distribution PA and end with a data distribution PB. And we can show that every time we do the reflow, the global curvature measure will uniformly decrease. Why this happened? Intuitively, we can think that the reflow always removes some intersection among the trajectories, which will always result in a lower curvature. And the formal proof can be done by applying Jensen's inequality. In particular, we can show that if we have infinite many times reflow, then we can always push that global curvature measure to be 0. And in this case, since at each point there's no curvature, the flows will become linear, and the flow will stop updating the coupling Q. That basically means the Q becomes a fixed point. And in the top example, it basically shows this fact clearly. If we have already end with this coupling, no matter how many times we do reflow, nothing will change. That's a warning for practitioners. So in practice, reflow basically relies on training neural networks to estimate the marginal ODE path. But neural network estimation always has some errors, and these errors will accumulate as the number of reflows increases. Therefore, there is always a trade-off between errors and reflow linearity. So basically, we need to end at some certain point to preserve the image quality. But in some special case, for example, the marginal distribution of my data distribution has a closed form expression, like for example, Gaussian distribution, then we definitely have some alternative method to avoid iterative reflow. I put the reference here, and interesting audience can have a look after this talk. And I want to discuss a little bit about its relationship to the optimal transport. So the optimal transport plan is actually a coupling connecting p data distribution of A and p data distribution of B. By definition, this coupling will satisfy the marginal constraints automatically. And we can show that the coupling induced by the optimal transport scheme will always give the linear marginal flow. That basically says the optimal transport coupling is always a valid solution to minimize the global curvature of the flow. But the converse is not always true in general. To show this, I gave a simple concept examples here, basically connecting two standard Gaussian distribution using linear flows. In the first one, it is the identity transformation, and of course, it's the optimal transport scheme. But for the second one, we introduce some rotation. Although it is still linear, but it's no longer optimal transport. Well, here's a contact example in real world, which is Canton Tower in Guangzhou, China, which is the tallest tower in the world from 2009 to 2011. And actually, as we can see, although this shape is elegantly banded, all the steel roads to build the tower are actually straight. Well, it's very similar to our contact example case. All right, this is the end of the part 2. For part 3, I will discuss some interesting results about structure preserving flows. So what is a structure preserving flow? Roughly speaking, a structure preserving flow tries to leverage some intrinsic symmetrical properties of data distribution to generate samples obey some invariant or equivariant properties. So, for example, the image distribution are always assumed to be invariant on X-flip, and that is the reason why we use X-flip to do the data augmentation when we train models. And what is equivariant properties? Let's consider a image denoising model, in which case we have input blurry image as an input, and we expect the model to output a clear version of it. And if the model is assumed equivariant, then in this case, if we rotate the blurry image by 90 degrees, we assume that output clear image should be rotated by 90 degrees as well. So why structure preserving property is super important? Here's an example. So in medical image analysis, all clear images are not always possible. For example, if we want to have a high resolution X-ray images, then we basically need a really high X-ray dose. This will kill the patient. Then instead of to have a trade-off between clear image and a high X-ray dose, we can train a model to perform the denoising task. And in this way, we can just simply take a blur image of the patient first, and then we use the model to obtain a clear image afterwards. And another motivation would be like, in general case, in medical field, doctors want more accurate results by obtaining different modes of the pictures, like X-ray, MRI, ultrasound, or CT. But in sometimes, not all devices are available in a hospital, and sometimes patients cannot take some tests. For example, patients with implanted devices cannot take MRIs. And in this case, a cell transferring model could help. And in medical image field, it's always required that the denoising and cell transferring models are perfectly equivariant. That basically means if I rotate an image, for example, a blurry image of cells by 90 degrees, I want the output image to be rotated precisely by 90 degrees as well. Why this is the case? This is because most medical image tests are designed to be invariant on the rotation and translation for diagnostic consistency. So basically, we don't want rotating an image of cells will change the diagnostic result from a benign to malignant if we want to detect the cancer. And to ensure the consistency after adding or denoising or cell transferring components, we basically want the components to be perfectly equivariant. Otherwise, if we rotate an image or flip an image, the component will generate some new features we didn't expect it if we do not rotate it, then probably the detect algorithm will generate some opposite result. So the question now becomes, how can we build a structure-preserving flow-based model? We basically derive some theorems, which is informal and simplified, to characterize how can we derive a structure-preserving flow-based model. Roughly speaking, if we have a group of functions that satisfy some group properties, basically we assume if one element exists in this set, we assume that its inverse also exists in this set. And any composition of the elements of this set will always result in an element in this set. So a simple example for this kind of group is the group consists of two operations. One is X flip and the identity matrix, identity function. Then in this case, if the identity flip has the inverse X flip, and we can easily show that this requirements can be automatically satisfied. Then under this setting, we can consider a diffusion process, take the form like this, which basically has a drift term conditional on an additional condition Y. And for a concrete example, we can consider Y and X0 to be a blurry image, and XT to be a transition from blurry image to a clear image. And we can assume that we also assume that if we flip the blurry image, and this transition invariance will be preserved as well. In our simple example, this is automatically the case because both X0 and Y are blurry image. So if we flip one, the other one will automatically be flipped. Then if we want XT to be equivariant with respect to the condition Y, then we need to guarantee that the drift term will satisfy some equivalence property as well. And why we want this to be the case, let's consider a special case when t equals 1, which corresponds to the clear image corresponding to the blurry image Y. Then in this case, we want the case that if we flip the blurry image, we want clear image to be flipped as well. And if we can guarantee that the learned drift term can satisfy this property, then if we rotate the input blurry image, the output clean image will be rotated as well. So this is intuition I just mentioned. And to sum up, the theory basically says if the drift F for sampling must admit some equivalence property to ensure, then we need to, if we want the model to preserve some perfect equivalence, we need to assume that the drift F we use to derive our model must satisfy some equivalence property. So how to achieve this in practice? We need to design a neural network model to satisfy these equivalence properties, and then we can achieve some perfect equivalence properties of our model. Here's a simple demo. If we apply our framework to design specific equivalence models. Here, what we are doing now is to transform city image to a pet image. And this is our model. And I2SP and pixel to pixel are two baselines we use for comparison. And to obtain these two plots, for the first one, we basically just simply feed the model with the reference city image, and we present output of the model directly. And for the right plot, what we do is to first extract the reference city image and send it to the model, and we flip the output of the model and present here. So if the model is actually equivalent, then we will assume we will expect that these two images are identical. So we take the difference of these two images, and we can see that for our model, which apply our framework, we will always obtain a black patch, two black patch. This basically means our model can be guaranteed to be perfectly equivariant. But for the baselines, since they don't have this equivariant property in theory, so we will have some white pixels here. So basically means if we flip the images of the input, then the output will be changed a little bit. All right, this is the end of the talk. Thank you, everybody.
Yeah, cool. Do we have questions for Hoye?
Hi. Hello, can you hear me?
Yes.
Yep. I have a question. Like in section 1, you mentioned like the two bridge model ODEs, like forwards and backwards, like xt minus a over t or xt minus b over 1 minus t. Like I feel like we know the analytical solution in a distributional sense, but when I'm integrating those using like Runge CUDA, then like it's difficult to solve these numerically because 1 minus t or t approaches 0. I was wondering if you've looked into methods of how to avoid that issue.
Oh, so when you do the estimations, so okay. So you are talking about the sampling part or the training part?
The sampling part.
Okay, so for the sampling part, we won't end with t equals 0 case. We will stop a little bit in advance so that we don't really need to solve the numerical error in practice. Yeah, that's probably a general way we do to deal with this problem. Another way we can deal with this is that we have much denser step size when we approach to 0, so that we will do more sampling doing that equals 0, approximately 0 case to improve the sampling accuracy. That's basically two ways I see in practice to resolve this problem. Yeah.
So I have a question.
Yes.
So you showed that in the version 1 and the version 2, the version 2 was not decoupled as like version 1. Yeah, it should be the next slide.
Okay.
Can you go to the...
Sure.
Yeah, so like from, if I understand correctly, version 2 is not what we wanted, right?
Yes, it's usually not what we wanted. If we want to keep the coupling, we cannot use version 2. Yes.
Yeah, and then that's why that brings us to the rectified flow.
So rectified flow is a limiting case of version 2. Yes. So what I would say is rectified flow setting cannot preserve the coupling between x0 and x1. But if you want to do reflow or those kind of tricks, you basically want to marginalize the drift like what we show in version 2, right? And
wait, so rectified flow and reflow is two different things.
Actually same thing.
Okay.
Because you in rectified flow paper, you need to use reflow tricks to linearize the trajectories, right? How can you linearize it? You need to in each iteration, you need to marginalize the drift in some way. And how to marginalize it? You basically need to marginalize it over the all endpoints, like both starting and end points, so that you can mix up the flows, right?
Okay.
So if you want, for example, okay, so So if you start this point, if you do the reflow, you want to end with this point.
Mhm.
That I show in part 2. And you start from this point, you want to end with this point. That basically requires to not keep the coupling. If we keep the coupling, we cannot do this, because if we keep the coupling, every time we start from this point, we are always end with this point, and there's no way for us to do the reflow anymore. That's the kind of a feature. That's actually sort of a feature.
Can you repeat again? Like, can you repeat again for the previous sentence? You mean you say about like the version 1?
Yes, for the version 1, if you start from this point, you will always end with this point because we keep the coupling, right? But for the version 2, if we start this point, we will end with this point because we do not preserve the coupling, because we average the trajectory at this point. This is more of a view if we check the ODE version as I showed in part 2. In part 2. So when we do the reflow, we want to average the drift at this point, right? And then the ODE drift will be diverted at this point, and then we'll start from A1 and end with B2. But if we keep the coupling, we will always start from A1 and end with B1. Then reflow will not happen, and then we cannot linearize the flow anymore, like what we did in reflow, in rectified flow. That's the reason why we have to stick with this setting if we want to do reflow in rectified.
So basically, it's one is conditional, like the other is not conditional, right?
The other one is not conditional.
Oh, yeah. I see. So in what circumstances do we need to preserve coupling? Because like in image-to-image translation, right? It's more like an optimal transport problem where you don't actually have like a coupling
Yes.
preservation necessary, right? So in what kind of scenario is this a problem?
For example, if you mean if we lose the coupling and we want to do some, say, denoising task, like starting from a blurry image of hues, we always want to end with the corresponding version of a clean image of that use. I don't want to end with something else. Then I need to preserve the coupling. Yeah.
Okay. So you were saying that if it's like it's more like a conditional kind of task, then the coupling needs to be preserved. While like unconditional, like text to or like unconditional image generation, then the coupling is not needed. Okay, I see.
The coupling is not needed.
Oh, so in
a very special case, for example, let's consider the diffusion case. We just interpolate between a Gaussian distribution and a data distribution. Then the coupling is meaningless, and then we don't really need to care to preserve coupling.
I see. Then does it mean that like if we are doing like style transfer or image editing, we cannot use rectified flow? Is that?
Not really. Because for example, we probably don't have the coupling in the original data set. We have no prior knowledge about this. Then we don't need to enforce the coupling because it's not natural. Then we probably would rather just let the model to figure it out what the proper coupling is automatically using the rectified flow setting. Yeah.
Okay. So you like in the medical image task that you have is so that one requires coupling, right?
Yes. So we basically implement the BM, the coupling preserve the version of the backward process.
Yeah. Oh, okay.
Yeah.
Sounds good.
Okay, maybe I'll add that on a particular data set, usually you don't have a coupling, right? That will require a lot of human annotation. And one way to deal with it is when you do not take the coupling into account, and when you do the editing on the images, you will have to limit the time horizon, right? If I add noise and I denoise, I don't add too much noise. I don't denoise for too long. Otherwise, it will become a new image that's completely irrelevant to my original image, right? So this is the other way sort of to deal with it. Now, if you have a coupling, like in the bridge model, it doesn't matter how long you denoise, you will not destroy anything, right? So that is another difference that people do in practice to sort of limit the impact of not having a coupling. And I think the other thing to that this is a question. The other thing that always bothers me is if you look at, I mean, we kind of understand what the bridge model is doing now. But in terms of rectified flow, right? Like this picture, what you show here, it's a very nice picture. And we also know when you do the reflow, like what do you preserve? Right? When you do a reflow, we know you're not going to preserve the coupling between the starting point and the end point. We also know you're going to preserve all the marginal distributions at each time point.
Yes.
Right. So the marginal distribution at each time point is preserved, but the joint distribution between two time points, they are not preserved.
Yes.
Right. I think it would be very interesting to understand like what precisely is lost and what precisely is maintained when you do this reflow process.
Yep.
Yeah. Because right now I think for many tasks, all you care about is probably the marginal density, maybe even the density at the two endpoints. That's what you care about. But there are also maybe tasks where you care more about the interactions, right? And in that case, this reflow process may not be the best thing you want to do.
Yes, I agree. Actually, these two examples basically shows that reflow may not always give the same fixed point at the end if we do it many times. So it remains questionable that what reflow is truly doing if we do it infinite many times. Yeah. So it's not a well-defined question to be honest at this point, and yeah, we don't. Yeah, it's just an open question. And it's another question is.
I like the picture you showed later. The actual.
Oh yeah. Yeah, the actual picture is really nice. Yeah. Actually, I presented two pictures first because I don't want to, because I think this will take too much time for me to plot it, but later on I succeed and then I put them here. Yeah. Yeah. Actually, I don't know what's going on because actually I derived this kind of example by myself at the very beginning before I checked kind of paper. And my motivation was from this picture actually.
Okay. Cool.
Yeah, any other questions?
So yeah, maybe a very dumb question because I haven't implemented a rectified flow on my own. So how is reflow being actually implemented? Is it like during training or is it during inference?
It's during training. So what they usually do is like first I train a neural network to learn the first marginalized ODE. And I use that ODE to do the reflow and generate new coupling.
How do you do the reflow? I think that's what who is asking.
To do reflow, we basically
So you calculate some like expectations and stuff like that, or?
Yeah, so basically what we for the first iteration after coupling, like starting from this point to this point and with this point and with this point and with this point. And then I will have a marginalized ODE in KN, and then I can use a neural network to learn it, right? It's like that use regular drift matching, something like that. And then to do the reflow, I will sample an image from my data distribution at this point, and I will follow this reflow, this ODE path, and then we'll end with the image here, which is in EB. And I will do the same thing for each sample in my data distribution. and then I have a reflow coupling, right? And then I will use the reflow coupling to train the second marginalized, to estimate the second marginalized ODE, which is train the neural network from scratch again and again and again. And then I will do the reflow. That's the reason why I'm saying there's a warning here, because every time you do reflow, you basically need to retrain a neural network from scratch. And this estimation on the marginalized ODE will not be accurate. So basically you will have some errors accumulated when you keep doing reflow. And at the end, you probably will not end precisely with some data distribution at this end. And then image quality will keep dropping. So that's the reason why we have to have a trade-off between errors accumulated and flow linearity. Yeah, that's the reason why I mentioned here.
But there's one step I think you missed. So namely that once I learned the rectified flow, when I do a reflow, I will have to solve the ODE for each training data point.
For each
Right.
FTT, yeah.
Yeah, so you have to solve the ODE for each training point in your data set. You have to solve the ODE with this data point and the starting point, then you get to the end point. Right. So you have to solve the ODE many times. And then you have to learn using the neural network again. And then you repeat, right? So it's very expensive.
Yes,
It's not cheap.
it's extremely expensive. Yeah. I think if you do it in the latent space, it's probably cheaper, but the same problem will be preserved.
Do they actually do reflow, like when they are training like this large diffusion model, the large flow model like Flux or whatever, or SD3? Do you know whether they are actually doing reflow at all?
I'm not really sure, but
because like if I look into their papers, they seem to only be like minimize the algorithm one, and so the loss function, right, where x1 minus x0 minus something, right? They seem to only like minimize that one. I don't see they have like a special step of like doing reflow kind of thing in at least in some of the flow-based image generation papers.
I see. So in usual case, if we don't do reflow, we usually call the algorithm flow matching, because flow matching is basically the same as the first iteration of rectified flow. Yeah.
I see.
Yeah.
Flow matching.
That's a sad story.
Okay, so flow matching is like the first step of
rectified flow.
Oh, I see. So rectified flow is more. Oh, okay. So it has a special meaning, basically. That I specifically point to the fact that you do reflow, right?
Yeah.
I see.
I think rectified flow is just flow matching. When you do reflow, you say you reflow. Is that right?
Yeah. When you do reflow, you basically change the coupling, but in flow matching, you do not change the coupling. That's the only difference.
So this is why I thought rectified flow, to me, is just the same name as flow matching. There are no
but they don't have. But
it's just a special case of flow matching.
No, flow matching is a special case of the rectified flow, I would rather say, because
depending on how you say it, they are depending on how you look at it. You can say flow matching is a special case of rectified flow. You can say rectified flow is a special case of flow matching.
But anyway, in flow matching, they do not introduce reflow to linearize the trajectory. I think that's the part. That part is missed. So
So the flow matching, they never do reflow. So the confusing part is in the rectified flow paper, this is a Chinese paper, they introduced rectified flow, which is basically the same as flow matching. And then in the second part, they introduced the reflow procedure. That's why when you say rectified flow, usually it's referred to Chinese paper. It does have reflow there.
I see. So
but I don't think people use reflow that much. That's my impression. Yeah. It's too expensive, probably.
It's too
Then
expensive.
you're not
But
using reflow, like the curvature is still there, right?
Yeah.
It's
yes, exactly.
what's its advantage over like the previous DDPM kind of stuff?
Oh,
Or
it's easier, I guess. It's OD.
It's
right?
so
oh, it's
the
easy?
usually it's easier to be trained as they claimed, and it's you can use because everything is in ODE, you can use sophisticated ODE solvers to solve it.
Yeah.
While in DDPM or those kind of things, you basically need to solve an SDE, and sometimes more complicated. And we don't have much knowledge about that. We basically use Euler method for them to solve it.
Yeah.
And
The other thing is you do ODE, it's deterministic. Right. So if you run the same procedure twice, you get the same result. Now, if you run DDPM, you run it twice, you may get different results because there's a noise inside.
Yeah, but you can train with DDPM, but like sampling with DDIM, right? That's
Okay. Yes. You can
that's
do
the tradition, and then
Yeah.
like, and then and then gradually like the community started to adopt flow-based models, and then they totally kind of ditched the diffusion-based ones. Yeah, I'm just wondering, like, if they are not doing reflow, what is the advantage here? Why is the community suddenly changing to the flow-based method?
Mhm.
Because it doesn't seem to improve like the curvature thing, right? Yeah.
Right.
I don't know. Basically, I have a feeling like they usually say if we implement the deterministic flow version, the
Mhm.
training becomes much easier and it converge
Okay.
faster. Yeah, that's what they have said.
I see.
And actually I mentioned a paper here. And actually I mentioned the name at the bottom. And
Mhm.
they have a very special trick to avoid reflow, but still can linearize
I see.
the trajectory. But the only limitation here is that we need one side of the distribution to be a closed form has a closed form density expression so that you can make sure some constraint is satisfied. Yeah.
There are two other reasons, maybe. One is how you already mentioned. The ODE solvers are much more mature than SDE solvers.
Yeah.
The second thing I think is when you do the SDE, it just seems too complicated for people. You have the forward process and then you have the reverse process, right? And then if you're not careful, you might write down the reverse process incorrectly. And then you have to get the DDIM version if you don't want the noising. It's just too complicated for the ODE or the flow matching part. Because it's ODE, it's deterministic. If you want to reverse an ODE, you just traverse the trajectory backwards. There's nothing complicated. The forward time as ODE and the backward time ODE are completely the same. You just change the starting point. That's all you need to do. So I think that's probably
I see.
what people feel like more comfortable with.
Okay.
But on the other hand, I think this is what how you maybe were thinking as well. There might be advantages to do an SD procedure because when you do an SD, you add noise in between. That noise might smooth things for you. We don't know how to quantify this yet, but I think there are cases where the ODE may be ill behaving, but if you turn it into SD, things might get better.
Okay. I see.
Yeah.
Okay. So the other advantage I can think of is like if you do flow-based models, you don't need to design the noise schedule,
Right.
And then if you
Right.
if you do like the DPM or DDIM, like you do need like the noise schedule to be defined, and that's additional work that you need to.
Yeah.
I see.
But even if you don't need to define noise schedule, but you still need to define the sampling schedule of T when you do the training. It's like you need to probably sample T close to 0 more frequently so that they have a better estimation at that part. And you don't need to train too much for big T because the trajectory is not that
You mean for
then
flow-based models or?
for both, yeah.
For both,
flow
yeah. Like the time intervals, need to be
yeah.
taken care of. Yeah. Okay. I see.
But for the sampling, because we have very sophisticated ODE solver, we don't need to design a time sampler for the sampling part. But for the FE, you have to design manually. Yeah, because ODE solver can proactively consider curvature of your ODE so that it can just do something automatically to guarantee the evaluation error to be very small. But if we are dealing with the SDE, then we need to deal with those sampling steps proactively. Basically, it's kind of fixed when we do the sampling, and usually it's much more complicated. Yeah, because we have less knowledge about SDE.
Okay, yeah, sounds good. Thank you for the answer.
Yeah.
Cool. Do we have any other questions? So anyone here going to New Lips? No one?
My whole lab is going. My whole lab is going.
Oh, cool. So you and Max are going there. Okay. Cool. Okay. I guess if there's no other questions, maybe we can stop here.
Okay,
Thanks, Hao Ye.
sounds good. Yeah, Hao Ye, it would be great if you could share the